Right. Good afternoon, everybody, or good evening, the Europeans. We're starting the last session of today, namely the session on heavy ion physics and precision QCD. The first speaker would be Barbara Jacak from University of California, Berkeley, who will tell us about almost exactly this. It will be, well, the QCD from heavy ion physics and what have we learned out of it. Barbara, I will warn you after 20 minutes, then you will have another 5. Please go on.
So thank you very much for the kind introduction, Barbara, and for saying my name correctly.
Yeah.
Rare treat, and good morning, everyone. Let me share my screen. And let me go to full screen. Do you see my slides? And do you see all of them?
We do, and we hear you correctly. Please go on.
Very good. So it's my pleasure to tell you what we've learned about QCD from heavy ion physics so far. And if I can figure out how to advance the slides here, I will do that. Can you also see my cursor?
Yes, we do.
Great, thank you. Oh dear. I have had this problem before. And it doesn't always, very strange. Very good, so I will talk about quark gluon plasma, a little bit how we make it. And then I'll talk about some of the measurements and theory that allow us to have some, learn something about QCD. In particular, I'll talk about collectivity. I'll say a little bit about hadronization. And I will share some lessons we've learned from jet probes of hot, dense QCD matter. And of course, some conclusions, which I warn you include open questions. So heavy ion collisions are available at the LHC at CERN and at RIC at Brookhaven. And in both cases, we collide heavy nuclei to get the maximum temperature and volume of quark gluon plasma. The energies of the collisions are in the hundreds of GeV to several TeV per nucleon range, so the temperatures are high. Now, what happens in hot QCD matter? Well, as you already saw from the event displays, many particles are produced. And so from the deposited energy, you reach a very high temperature. The many produced particles give you a very high density. And then the potential between quarks is screened by the produced partons. So here you see a plot of the interquark potential as a function of the distance between a pair of quarks, heavy quarks in this case. And the gray line is what the potential looks like in vacuum. As you increase the temperature and therefore the parton density, what happens is the potential starts to get screened, as you see with these colored curves that correspond to ever higher temperatures. And eventually, at some critical temperature, the potential is entirely screened away, and you then expect a phase transition to a deconfined quark gluon plasma, where you no longer have any hadrons. According to lattice QCD calculations, which is also where these curves came from, this critical temperature should be around 160 MeV or so. Now, looking at these rather dense event displays, you may be wondering how we can study the quark gluon plasma properties and learn something about QCD. Well, of course, all we can do is use the particles coming out. I like to think of the particles coming out in 2 flavors, following the, or 2 types, following the lead of plasma physicists. At low PT, and by low, I mean somewhere below 5 GeV or so, these are particles that are actually radiated from the bulk medium. So they're particles from the plasma itself after it freezes out. And particle physicists would, plasma physicists would call this internal plasma probes. At large energy, either large momentum or large mass, you then have a scale other than just the plasma temperature. And these are probes then that interact with the plasma. You can think of them as an external probe. And they are, of course, auto-generated within the collision in the initial hard scatterings. And that is calculable with perturbative QCD. And we have measured and compared and shown that this is true in many cases. Of course, any good measurement has to have controls. We do have a very good control probe for studying QCD in the plasma, and those are photons, which of course don't feel the strong interaction. And our control system are proton-proton collisions, where you do not expect to make some significant volume of quark gluon plasma. Now, of course, the nuclear collision time, as everyone in this conference knows, is short, a few times 10 to the minus 23 seconds. And I have here a little snapshots from a movie of the different stages of a heavy ion collision. Here you see the Lorentz contracted two nuclei coming in towards one another. They, at their first interactions, you have initial scatterings, including some high momentum transfer scatterings. And then you come to a time of many secondary collisions. And that's when the primary particle production is thought to occur. And so you're going in this lower case here, on the phase diagram of nuclear matter, you're going from a baryon density of normal nuclei to a much higher temperature, crossing into the quark gluon plasma region. Of course, the system continues to expand, especially longitudinally at about the speed of light. We also know it expands transversely at 0.4, 0.5 times the speed of light. That causes, of course, the temperature to decrease. You still have a lot of secondary collisions going on, presumably, and so one could expect that the density may continue to increase a bit more. Eventually, the system cools enough that you start to rehadronize and come back to normal nuclear matter density with many, many particles in the final state. So just to summarize a couple of the big lessons from quark gluon plasma, we have observed many things that tell us that the hot QCD matter is strongly coupled, not just that it interacts via the strong interaction, but there are many particle interactions. It flows hydrodynamically with entropy over, with a viscosity over entropy density that's very close to zero. Now, you often will see viscosity over entropy. That's basically it's the viscosity per particle, but since the number of partons is not conserved, entropy is the best measure we can have. This very low viscosity per particle, it's even lower than liquid helium and lower perhaps than ultra cold atoms, is why we think of the quark gluon plasma as a nearly perfect liquid. Oops, let's see. We also have learned that the quark gluon plasma is very opaque to color charged particles, even to heavy quarks. What you see here is the ratio of the of particle spectra transfers to the beam direction, what's observed in lead-lead collisions compared to what's expected from proton-proton collisions. And you can see, so should there be exactly what you expect, the data would all fall at 1. The red here shows, the red with the yellow systematic uncertainty boxes shows the charged particles. And you can see a suppression that is quite large, becoming as large as a factor of 4 or 5. Interestingly enough, you also see that the heavy, the mesons, including heavy quarks, D mesons here in black and B mesons here in blue, are also suppressed. So that indicates a very large energy loss to the plasma. I'll come back to the heavy quarks. Now, you may be wondering about what happened. Are we doing this right? If you put photons, WZs on this same plot, they are right around 1. So let me then talk a little bit about collectivity. How do you actually measure collective flow in a heavy ion collision? Well, here, let me explain this. Here's a cartoon of a pair of heavy ions that have interacted just a moment ago at some finite non-zero impact parameter. And you can see that the overlap region has this sort of almond shape. And that's, of course, where the particle production takes place. If you look at it from the beam's eye view, you can see that in coordinate space, you have an asymmetry, and therefore you would expect there to be some pressure gradient with a larger pressure here in the x direction than in the y direction. Now, that kind of pressure gradient would translate into momentum space as an anisotropy, that there's a slight preference for particles to get a boost in the x direction. And so that's something that we can, in fact, look for experimentally. The way we do that is by looking at the azimuthal opening angle distribution between every pair of particles. And if there is no anisotropy, then that opening angle distribution, that correlation function should be basically flat. Here you see some examples, a couple of different impact parameters, a couple of different momentum ranges of particles, and you see that it is not flat. It actually has a modulation, and So we then can subject this to Fourier analysis, and the second Fourier component corresponds to the amplitude of this modulation, and we call it elliptic flow. If you have this is supposed to be a phi, by the way. If you have a non-zero elliptic flow, it means that your initial almond shape here would translate into a cylinder that is anisotropic in the way that's shown here in red. So we've made that measurement. You already see from the nearly raw data that the amplitude is not zero. If you plot the amplitudes here as a function of the impact parameter, or related to the impact parameter with peripheral collisions here and central collisions on the right-hand side, you see that the amplitude is actually quite large, becoming as large as 7 or 8%. It's larger for peripheral collisions because the initial asymmetry is larger, and it becomes approaches zero for central collisions, where you get a roughly spherical overlap region. The red bars here are initial predictions from hydrodynamics, and you can see that once you have more than a few particles participating, hydrodynamics does very well. Now, a couple of interesting things. The first one is that if you want to get the elliptic flow of pions and nucleons correctly, you need to assume that the system spends some time in the quark-gluon plasma phase. You cannot do this with a purely hadronic equation of state. You also need to start your hydrodynamics very quickly. And the fact is that to get anywhere near the data, this only works with a hydrodynamics calculation with a very low viscosity over entropy ratio. And that was our first hint that, well, our first indication that there is quark-gluon plasma and that its behavior is interesting. Now you can better quantify the viscosity by using the higher Fourier coefficients as well. And you may be looking at this overlap region that is almond shaped and thinking, well, wait a minute, how can you ever get an odd Fourier component? Well, you do, you can and you do, and that's because the nucleons, of course, move around inside the nucleus. And so the location of where the nucleon-nucleon scatterings take place fluctuates event by event. And so in any given event, you can also have a triangular flow, namely a third Fourier component. And so what you can see in the plot here, it's from a hydro calculation comparing the values of the Fourier coefficients from 2 to 5 in viscous hydrodynamics over ideal hydrodynamics. And you can see that by reproducing with hydro multiple of the Fourier coefficients, you get a much better sensitivity to the viscosity over entropy ratio than just from V2. And this actually has been done by a number of different calculations. And so we know that the viscosity over entropy ratio is somewhere in the vicinity of about 0.1. And that's why it was where it showed up on the plot I showed you earlier. Now, we thought we understand many things from this, and then nature gave us an interesting surprise. Namely, we also see hydrodynamic flow in very small systems. Shown here is proton-gold collisions and deuteron-gold collisions. These are rather central proton and deuteron-gold collisions. And the data are here in the data points. The blue and red lines are calculations with hydrodynamics, taking into account what you see here below, namely the fluctuations not only of the where the nucleons are, but also the quarks inside the nucleons. Now, what's going on? We see, again, collective flow. We see that it is, again, seeded by the initial geometry, but one has to wonder, how could pressure have time to build up before this tiny system evaporates? So there's a lot of work going on to understand this mystery of the rapid hydrodynamization. And I just want to note that one of the things we have probably rediscovered is that full thermalization is in fact not required for hydrodynamics to work. Now, of course, hydrodynamization is very difficult to measure, yet it's one of the key questions. So what could be going on? Well, is there coherent scattering that plays a role? This is something that we're trying to study. It's pretty tough in quark gluon plasma, I think, but the partonic interactions in hot dense QCD and cold dense QCD at small x should be quite similar. And so that, I think, would be a nice way to study, to look for evidence of coherence without the final state effects that we have in hot dense QCD. We have learned that the very rapid longitudinal expansion, that drives a loss of the initial state memory and causes mathematically a hydrodynamic attractor. This could, in fact, be causing the out of equilibrium hydrodynamic behavior. Of course, the PP and P-gold and D-gold collisions don't hang around as long as a lead-lead or gold-gold quark gluon plasma. So there's much less time for equilibration. Maybe that's the answer. Or perhaps what we're seeing is impact of pre-existing many-body interactions. And there again, studying nuclei at very small x would be important. I want to say a little bit about hadronization, because in studying hadron formation from quark gluon plasma, we observed something maybe surprising. If you plot the elliptic flow, the second Fourier component V2 per quark, then you find that you have a universal curve, near universal curve between mesons and baryons. You see the proton, antiprotons, lambdas all fall on the same curve. Now, that tells us that the quarks, or the degrees of freedom when the collective flow develops, that's consistent completely with the message from hydrodynamics that I just told you. However, the thing that's also quite interesting is that it was discovered that if you make the hadrons by simply recombining valence quarks, or if you will, constituent quarks from a thermal distribution, you actually can reproduce the magnitude of the V2 for the different hadrons, as well as their transverse momentum spectrum. So a simple picture of dressed quarks being born of this flowing field and hadronizing by a relatively simple coalescence of co-moving quarks actually works. Of course, how the quarks are somehow dressed by the gluons is not exactly understood, but if you make that simple assumption, then you have a hadronization picture that reproduces data. Now, maybe that tells us that phase-space coalescence is how all hadrons form. I don't know the answer to that, but I think it's a question worth exploring. I'll say a little more about that in a moment. So let me turn then to transporting QCD matter. So I've shown you already that there's a significant energy loss by partons in the quark gluon plasma. We can quantify that by a variable we know as Q hat. Q hat is essentially the mean PT transfer per scattering divided by the mean free path of your parton in the quark gluon plasma medium. So you can think of it as the KT kick that the parton gets per unit length of medium.
Barbara, 5 more minutes, please.
Oh, my clock only says 18 minutes, but all right, I'll do my best. We constrain, so what do? How can we get Q hat? Well, we have to do a calculation with as close to QCD theory as possible, but includes a model of the expanding quark gluon plasma and calculate the partonic interactions in that. And if you do such calculations and then constrain the theory to agree with the measured spectra ratio of in lead-lead compared to PP collisions, and note this goes out to more than 100 GeV, then you can extract this Q hat parameter. And what you see are values that are between 1 and 2 for quark gluon plasma. It's temperature dependent, as it should be, because the density is temperature dependent. In a hot hadron gas, the Q hat value is maybe 0.4, and calculations show that in cold nuclear matter, it's significantly smaller. Now, more sensitive probe are jets. Now, why is that? Well, if you remember that a hard parton traveling in vacuum will undergo a probabilistic cascade of gluon emissions. Of course, in those emissions, total color charge and flavor are conserved, and the successive branchings are ordered in angle. Furthermore, the color coherence of the object, having started out with a single parton, suppresses the large angle soft radiation. And so if you look inside a jet of hadrons that comes from an initial high momentum parton, then you could imagine that what took place are a set of splittings like this. And what you see inside the jet is collinear hard radiation. And then the soft radiation is somewhat less collinear than the hard radiation. Now, you would expect this process to be modified inside a dense medium, and indeed it is. There's a dijet from CMS where they triggered on a 200-ish jet and then looked 180 degrees away in azimuth, and instead of finding the partner jet near 200 GeV, what they found was a 70 GeV jet that was kind of spread out. That is, of course, exactly what you would expect if you have this guy selects a parton off the surface, and then this one is the remnant of the parton that had to go through and interact with the medium. Now, of course, a complicated issue is this question of what is in a jet. Whoops. Do that to me. Okay, let's try this again. So a very important experimental question is, what is actually in a jet? Which hadrons belong to the same jet? The way to answer this is to use a jet finding algorithm. Everybody these days uses anti-KT, where you seed a jet with a hard hadron or a high calorimeter tower, and then calculate the distance to all the other particles weighted by 1 over KT squared. And that clusters softer particles with the harder ones. Typically in ion collisions, or even in PP, we use R of about 0.4. That's to allow the statistical subtraction of the underlying event, which in lead-lead is huge, as you can see from the event displays. Of course, that misses some of the parton's energy, so it's not perfect. However, we can proceed with this and then look differentially inside the jets to see what happens. Well, what's plotted here is the ratio of the parton spectra inside the jet, and the different lines correspond to different radii inside the jet. You can see here in black, right in the middle, there is no modification in lead-lead compared to jets in PP collisions. However, as you get closer and closer to the outer edge of the jet, you start to see an enhanced production of soft particles, here PT below maybe 4 GeV, and a suppression of the very high momentum particles, which is what you'd expect if you have a significant energy loss. So this allows us to, in fact, try to use these as well to both refine our knowledge of Q-hat, but also probe more deeply into the interactions of the partons inside the medium. This large enhancement, almost a factor of 2, could also be telling us that there's a medium response. We know also from CMS at CERN and from Phoenix at RIC that the jets get wider and softer in quark gluon plasma. And so we actually have observed this medium-induced extra soft radiation that you would expect that I showed you in the earlier cartoons. Now, if you want to do a perturbative analysis, of course, that soft stuff is in the way, and what one does is grooms the jet. The way you do this is you start with all of the particles in your jet, as I showed you before, and then you collect the particles into subjets using the Cambridge-Aachen algorithm. And then you use an algorithm called soft drop to groom your jets. Essentially, what you want to do is to remove the soft, non-perturbative subjets. And you do this by looking in each splitting. And if you have a branch that is less than some cut value, 10, 20%, then you drop that branch entirely. And what that does is it removes the soft radiation and the non-perturbative effects, and it allows access to the perturbative splittings that you're interested here, which are calculable in PQCD. Now, this has the other very nice feature that it also grooms away the underlying event. I would just note that if one wants to study hadronization, this soft stuff is probably a very good place to look because that's where your hadrons are forming. Now, the next to the last thing I wanted to mention is that we'd like to look at the collinear splitting and ask, do we see any medium-induced change in the hard gluon splitting? So to do that, we do the soft drop grooming, and then we look at the ZG, namely the split, the ratio that the softer one takes of the pair. And you can see this here measured by CMS and lead-lead and proton-proton collisions. Hard to see much from these plots, but if you take the ratio, you see that as you go from very peripheral collisions to very central collisions, that you do indeed see a modification in this first split. And that, again, we can use to constrain theory and quantify the energy and momentum transport in the plasma. The last slide I wanted to show is about heavy quark energy loss. Remember, I noted that the heavy quark energy loss is almost as large as that of the light quarks and the gluons. Now, this was actually a big surprise. If you look at the equation for the soft gluon radiation spectrum, given here, you find a dependence on this angle theta sub 0, which is the mass over energy of the radiator. The larger the mass, then you essentially close off some phase space that you can radiate into. You can't radiate forward, and that suppresses the small angle radiation and is known as the dead cone effect. So it was expected that heavy quarks would lose less energy than light quarks. The dead cone effect has actually been observed by Alice in charm-tagged jets in PP collisions using these jet reclustering techniques, what you see here is the ratio of D-tag jets over inclusive jets, and it's really the ratio of subjets as a function of the angle with respect to the D meson in the case of the charm jets and the high PT particle in the case of inclusive jets. And you do see a suppression at these very low angles. So one wonders, how is that consistent with this large energy loss of heavy quarks in quark gluon plasma? Does collisional energy loss make up for it? Or is there medium-induced radiation that fills in the dead cone effect? Stay tuned for the answer to that. So let me just then conclude. We have many body interactions in QCD that cause the plasma to be strongly coupled. And we've learned that the viscosity over entropy ratio is about 0.1. It's very low. We've learned that the system is very opaque to transiting particles. The kick on the particle is about 1 to 2 GeV squared per Fermi. You can think of that as how much energy gets sucked out of it. We've seen rapid hydrodynamization that we don't really fully understand. We see that a simple picture of hadronization works quite well. And we see evidence of parton splitting modified by the medium interactions. You see scattering induced radiation. We do see the dead cone effect in PP, and we're looking to see if it goes away in lead-lead, or whether it's collisional energy loss. And I just want to end with one more question, and that is, it leads one to wonder whether cold dense QCD matter is strongly coupled also. At very small x, the density of gluons is high, and perhaps we would see some of these same interesting features. And I personally am very interested in asking the electron-ion collider to help find out. Thank you.
Thank you, Barbara, for a very good talk. Lots of explanations for non-experts like myself. Now we have a little bit shorter time for questions, something like 4 minutes. So please raise your hands and or maybe write your question on a chat, if you prefer so. Well, there is a person from Stony Brook University, Niv. Please, Niv, go
on. In one of the slides, you spoke about V2 over the number of quarks and about hadronization of quark gluon plasma. Yes. I was wondering, does this change with collision systems, or is this all done in similar heavy ion collision systems like gold-gold and lead-lead?
That's a very good question. So this is for the most central collisions in this particular plot for gold-gold. When you do it in lead-lead at much higher square root of S at CERN, the picture qualitatively continues, but you do start to see some changes, especially here in the, some deviation, especially in the lower transverse kinetic energy region. So there is some other physics going on as well, but the general picture is, it holds.
All right.
Thank you.
Please,
Barbara, you probably gave that answer inherently in one of your comments, but I do want to ask again. In the hadronization, in the slide that you showed, the grooming of jets, yes, you commented that you can learn hadronization in the peripheral, in the soft region of that plot. What is the experimental control over that? How do I control an experimental situation in trying to study hadronization under different conditions?
Right. It's a very good question. My first order answer is, I don't know yet. My second order answer is that I would look actually not necessarily in heavy ion collisions there where I know I have a huge underlying event and lots of other stuff going on in the interaction of the jet with the medium. I would look in PP collisions to begin with, and maybe eventually in EP collisions, and see whether a very simple model of coalescence of partons in the outer regions of the jet where things are pretty soft, how well that works.
Okay. Thank you.
I don't yet know what the experimental difficulties will be there. There will be some.
Yeah.
We have to finish at this question now. So thank you, Barbara, again for your very good talk.
Thank
and
you.
Now I would invite Stefan Hoeche from Fermilab, who will speak about Monte Carlo generators and corresponding phenomenology. Please go on.
Yes. Hello, can you hear me?
Yeah, albeit not very clearly.
Okay. Is it better now?
Could you get closer to your mic, maybe?
Okay. I am a little closer to the microphone. Does that work now?
That is a little bit unclear in my opinion, but okay. Please go on.
Okay. Okay. Okay, so let's try this. So I will give a little summary on the recent developments in the Monte Carlo event generator world. And I will particularly focus on things that are related to deep elastic scattering, since this is DIS. Okay, provided that my slides will actually switch. Okay, good. So we know that deep elastic scattering is a precision test or precision laboratory for QCD, and this is reflected by the very many higher order calculations that have been performed over the many years, starting with the next to leading order calculations for the inclusive rate that were done at about the time when I was born, going to n-squared LO calculations for the inclusive rate, and nowadays we can do fully differential n-cubed LO calculations that were published just 3 years ago. When we look at event generators, the situation is a little bit different. We typically do simulations that are a little bit less precise, but on the other hand, more differential. So we start by calculating the hard interaction with something that we call generic matrix element generators, something like MATGRAPH, that describes the scattering at the highest invariant momentum transfers. This is a picture from PP collision. So you have the two protons coming in, and here as the hard interaction, a TD bar pair and the Higgs boson is produced. And this red blob in the middle here signifies the largest invariant momentum transfer in this reaction, and that is calculated nowadays typically at NLO QCD or electroweak, or in some cases also at next to leading order QCD, and deep inelastic scattering is one of the reactions where we can actually do this. Then the gap between the high invariant momentum transfer scales for the hard process and the hadronization scale is bridged by the parton shower, which simulates the emission of additional particles, gluons and quarks, and this is shown here in blue. And we can also simulate radiative corrections in QED using the Yanni-Fauci-Suva algorithm, which takes into account a lot more coherence effects than the parton shower is able to do. Eventually, once we are at the low scale where hadronization sets in, we employ phenomenological models like the cluster or string model in order to turn the quarks into hadrons. This is done collectively because of color connections and color reconnections that have to be taken into account. And then once we have primordial hadrons, the dark green stuff here, those are decayed into finely observed hadrons, and at every step along the way, these wavy yellow lines here signify how we add electroweak corrections, or more precisely QED corrections, using again the Yanni-Fauci-Suva algorithm. So I already said, in comparison to the very precise calculations that we have available, and this is just an example, the hard interactions typically at one order lower than what can be done in the pure fixed order world. So for the n-cubed LO precision in DIS, we can do n-squared LO precision in simulation, but we can add radiative corrections in an approximative way to arbitrary order using parton showers, and we can match this to the fixed order calculation such that we get a more or a better picture of the more exclusive observables that we may be interested in. And Monte Carlos are, as we know, one of the rare opportunities to actually include a model for heteronization. So again, I take deep elastic scattering as an example, as an example laboratory which allows us to probe our understanding of QCD dynamics. And this is actually a very interesting one, because if you take the inclusive reaction and you compute this in collinear factorization, it is quote unquote just a form factor. Of course, at higher orders, it's a very complicated form factor, but in principle, it's described by two variables, q squared and x, and there's no dynamics. But if you're interested in more differential measurements, it becomes a multi-scale problem and a very interesting one, because you have, for example, the QCD constant process, where you have an incoming photon and incoming gluon, and you can measure the transverse energy of the jet in the side frame. And indeed, there are two different scenarios. If q squared is larger than the ET of the jet in the side frame, then you are in the typical BIS scenario, where this form factor type calculation and addition of QCD radiation is actually reliable. But if the situation of the scale hierarchy is the other way around, and q squared is smaller than ET, then you want to actually calculate this as a QCD constant process, starting with the reaction that's depicted here. And what makes CIS different from all the other kits on the block is that the virtuality of this exchange photon here likes to live close to zero, so you are more often than not in this scenario, and you want to reflect this in your Monte Carlo simulation. And this gives us a very good feeling of how Monte Carlo simulations should in general be constructed in order to reflect the physics that's going on. So we already saw that we want to include as much higher order QCD as we can, and one opportunity to do so is to use a leading order merging algorithm. And this is sketched here. We start with the inclusive reaction at leading order. This is supposed to be the electron, that's supposed to be the hadron. And this red blob here is the hard matrix element calculation. We can add radiative corrections in an approximate way using a parton shower, and these blue dots here signify kind of a single parton shower splitting, kind of an effective operator, if you will. And alternatively, we can calculate this with a full higher order matrix element. So we just add an additional particle and calculate the full matrix element for that. Now, there is 100% overlap in phase-based coverage here on the diagonal, and in general in all the diagonals in this sketch here. And we have to account for that. So we cannot simply put a parton shower on top of this calculation, but we have to either subtract this piece that we overcounted, or we have to slice the phase-based. And typically in leading order merging simulations, this is done via phase-based slicing. And then because this calculation here doesn't include pseudocofactors, we also put pseudocofactors on top. And that gives you a very good way to describe the dynamics for very exclusive observables. If you do one more thing, so let's assume we start from this deep elastic scattering plus 2 parton simulation. In order to run a parton shower on top of that, or to match it to a resummation, we have to identify a parton shower branching tree that corresponds to a particular kinematical configuration for this matrix element. So this can be done by running something like a clustering algorithm, similar to KT algorithm. And this can proceed in various ways. One has to first realize that every particle, if it's light, can eventually develop a collinear singularity or soft singularity if it is a vector particle. So there are two options to go from here to a lower multiplicity configuration. I can proceed to the left by removing a parton and assign this parton as kind of a parton shower splitting having occurred. I can also remove the electron and come to a situation where I have a virtual photon, which is almost on shell, going into this process. And then if I proceed towards the left here, I can end up with something that we call a core process in this parton shower merging speech, which is really just inclusive deep elastic scattering at leading order. You have the electron coming in, you have a quark coming in, and you have two wimpy QCD additions that can be simulated or could have been simulated by the parton shower. But I can also end up in the situation and I go to the left here and then go to the right, and I have a core process which is QCD constant scattering, or I can even go all the way to the right here, and I can end up in a situation where I have two wimpy electroweak additions to the process and the core process that's pure QCD. And only the proper combination of all of those possibilities according to the correct branching probability in the logarithmically enhanced regions will give you the correct inclusive prediction for the full process. And one observable where this shows up very nicely is this measurement, which was performed by Hera, which measures the transport energy of the jet in the phi frame divided by q squared. So if this observable is above 1 or larger than 1, we are in the situation where we see mostly the QCD constant process, and this is where the measurement is taken here. Moreover, if we take this in the forward rapidity region, we are in the situation that I showed on the first slide, where you have large higher order corrections even from n cubed LO and even n4 LO configuration. And of course, we don't know all of them, or we can't simulate all of them, but we can include them in an approximate way by just taking the tree-level approximation into account using these merging algorithms. And you see how taking more and more tree level into account and going from the purple to the green to the blue to the red distribution here, you move closer and closer to the experimental prediction, to the experimental measurement with your Monte Carlo prediction, and it actually saturates. And of course, there are larger effects in the forward rapidity range than in the central range, and this is precisely what you expect. But it gives us the good feeling that we understand how to simulate this based on collinear factorization, and we don't actually need to include any additional effects. Now, eventually, we would also like to not only include tree level, but also get the inclusive rate for deep elastic scattering more precise, and this can be done by doing a higher order matching. So first, we can match our pattern shower to next to leading order calculations. The problems are the same. You start with this leading order type configuration or leading order type kinematics, and as you go to higher orders, you can add an additional particle. There is double counting with respect to the pattern shower, and this double counting has to be removed. In this case, because you want to get the inclusive rate correct, you usually don't do it by phase-space slicing, although it would be possible, but it would be less convenient. So it's done by subtraction, and there are two ways of doing so. One goes under the name of MC at NLO, and one goes under the name of Hoeche. They differ in the details, but the idea is essentially to remove the double counting and put the Sudakov in the right place. This gives you a very good prediction for the inclusive rate because it's NLO. However, I would caution that depending on what you measure, you may actually be better advised to use a leading order merge calculation. As an example, take the 2-jet rate in deep elastic scattering, and you have similar effects also at PP colliders. So it's always just about phase-space coverage. So think about it in terms of phase-space coverage. We take the 2-jet rate in deep elastic scattering for different values of the sum of the transport energies of the jet. So measurement is taken in 2 bins, and it's also taken dependent on Q squared. This is the high Q squared region as measured by H1, and this is the high and the low Q squared region. And there was this gap here in the calorimeter, so they are separated by some difference. And you see that the next to leading order match calculation here describes the high Q squared region very well, but a little discrepancy starts to emerge here at the lower end of the high Q squared region. And you can think of this match calculation being similar to the purple line on the right-hand side. And I'm sorry, the labeling is different here. This Nmax here actually means the one jet here. So if you extended this match calculation to the left, to the low Q squared region, it would actually follow this purple line, and it would not give you a very good prediction of the 2-jet rate in the low Q squared region. And this is because you don't cover all the phase space with the higher multiplicity configuration. And this is a generic effect that does not only occur in deep elastic scattering, but also in Drell-Young-Lepton pair production at the LHC. And the upshot is essentially, if you're interested in a very different differential measurement at high scales or with many jets, then it is a lot more important to take higher multiplicity tree level corrections into account than to take inclusive rate corrections into account. Not very surprising. Okay, you may of course say, I can also do a fully differential next to leading order calculation, and that's true, and It is relatively straightforward because the inclusive corrections are known, and we can use the projection to Born method and combine it with an automated NLO calculation for the budget process in order to put it into a pattern shower. The problem is, though, that these NNLO matching methods are currently not very efficient and computationally, and they are definitely not at the level that you could generate unweighted events with. However, you can calculate it if you can accept weighted events and have a large cluster available, and this is what you would get. This is in comparison to H1 high Q-squared data, and you can see a very good agreement between the Monte Carlo NNLO match calculation and the high Q-squared data for the inclusive, the dijet, and the trijet selection. And also for the low Q-squared region for the inclusive, dijet, and trijet selection. For the trijet selection, you see that the discrepancy starts to emerge here, and this would again be removed if you included higher order tree level, if you did emerging on this as well. But since you have up to 2 additional particles in the game here already, you're doing a very good job compared to the data. So where do we stand with all these simulations? Unfortunately, this is not for deep elastic scattering, but anyway, it solves the purpose. This is an example of a comparison of many of the techniques that I just showed on the previous slide, which are somewhat standard in today's Monte Carlo. This comparison has been done for vector boson fusion at the LHC. However, this is related to deep elastic scattering. It's essentially just double DIS, at least in the structure function approximation, which was also used here. And the summary of this slide is essentially that whereas differences are often observed when running different Monte Carlos or matching different Monte Carlos and comparing them to each other, if they are all used consistently, if they are used with the same parameter setting, the differences are actually very small. And more often than not, if you see a big difference, you should actually go to your Monte Carlo experts, which are in charge of this matching, NLO matching or whatever merging procedure, and ask where this may come from, because more often than not, it originates in the wrong for the pattern shower setting. This is exemplified here on the lower right-hand side in a comparison between actually a next to leading order fixed order calculation in 2 different Monte Carlo matched predictions. In blue, you have Boughezal plus Tutia 8, and in yellow, you have Boughezal plus Holwig 7. And you can see that they agree at the 10% level. There is a order of 15% deviation between them and the fixed order NNLO calculation, which means they do a very good job in describing even this event structure in the way that an NNLO calculation would, although, of course, they have larger uncertainty bands. And then there is this green line here, which is the same Monte Carlo as the blue line, so it's Boughezal plus Tutia 8, but run with a different pattern shower setting. And this pattern shower setting has the wrong kinematics, if you will. So even though you may think that you're running something that's next to leading order accurate, you're getting a completely wrong prediction simply from using a different pattern shower setting. And this is why I'm saying talk to your Monte Carlo experts if you are interested in using this. Because with a small switch that normally at leading order you would be allowed to flip, you may do something completely wrong at the next leading order because you're screwing up that matching prediction. That matching procedure. Okay. However, the lessons also in other processes, this is for glue to Higgs plus jet, where we also have, as a community effort, done a study very similar to that, is that if you do it consistently, you would see very little deviation between the next to leading order fixed order prediction, which is the reference line in blue here, and the Monte Carlo match predictions at NLO, which are the dashed blue and dash dotted blue here, which are hardly distinguishable from the blue. Okay. In this case, it's also kind of just a flat K factor compared with the NNLO, which is the green line here, which is also interesting. And also the Monte Carlo does a very good job in describing the jet shape as you would expect, and converges. Sorry, the fixed order calculation converges to this result from the Monte Carlo, which is shown down here, but that's kind of not the point I wanted to make on this slide. Okay, so with that, I'm going to the more recent developments in the Monte Carlo world, if you will. So on the hard interaction side, and I'm sorry, I will not say too much about this. What's currently very interesting. And of course, this is not an exclusive list. It's with a personal bias, so take it with a grain of salt. But what's very interesting is the extension of the capabilities of our automated generators to next to leading, when it comes to next to leading order electroweak. So electroweak is more complicated than QCD in many respects. So a full NLO matching for electroweak has not been performed yet because there is no, I would say, fully understood parton shower for electroweak at the moment. So this is currently in the works. Electroweak Sudakov summation is an interesting and hot topic, and this can be done in an analytic fashion and combined with the QCD parton shower. So you get the dominant effects of both in kind of a multiplicative or additive approach, depending on how you like it. This also plays into what I want to say here about the radiative corrections in the parton shower. So the matching at NLO, QCD plus or times electroweak is being in the works. What I will speak about is the extension of parton showers to next to leading order, next to leading log, and next to leading color and beyond. This is a hot topic. And what's also interesting, but I will not say anything about it, unfortunately, because I'm not an expert and couldn't get all the material, is hadronization at finite number of colors, which kind of has an interplay with what I want to say here, and then QCD environments and collective effects.
Stefan, you have 5 more minutes, please.
Okay, I'll try to make it. So in 2018, the group around Gavin Salam performed a very careful analysis of the logarithmic structure of parton showers and identified 2 common problems with mostly dipole showers, but also other showers. And the upshot is that there is a problem with kinematics, which is sketched here. So what is shown here is the ratio of the transverse momentum of the second emission over the first emission in the strongly ordered soft region, which is kind of at the bottom of this plot. And in this region, you find that there's an azimuthal correlation between the 2 emissions if you use an inappropriate recoil scheme, which is the kinematics reconstruction when you go from on-shell to on-shell partons and the emission of an additional particle. And this correlation here should not occur if the radiation pattern for arbitrary observables, in particular KT type observables like the jet broadening in the plus and minus or things like that, are to be described correctly and in accordance with the next to leading log analytic result. The other problem is that the average color charge of an initial QQ bar dipole in an E plus and minus to jet or in deep elastic scattering is not reflected correctly in commonly used parton shower or more specifically dipole shower approaches. And this is kind of sketched in these 2 figures here. You have the Lund plane where you have log PT going up and the rapidity going to the left and right. You have the phase space for the initial QQ bar pair as a Lund triangle, and if you have a single gluon emission here, it comes out as this wedge and creates additional phase space for emission of the gluon. And the correct picture is that in the back plane of this Lund plane, you should have, or for the phase space that is kind of described by the back plane of this Lund origami diagram here, you should have emissions associated with a color factor of CF. Whereas in this wedge region here, you should have them associated with CA/2. But what the dipole showers do is, because of their phase-space partitioning, they actually describe a part of the backplane with a color factor CA/2. Now, of course, CA/2 minus CF is not very big. It's 1 over NC suppressed, but you can actually do better, and we will see in a minute how. But let's first look at the kinematics problem. So, oh, I'm sorry, this should actually say kinematic problem here. I'll correct this in the uploaded version of the slide. So the kinematic problem can be solved by partitioning the antenna radiation pattern of the parton shower and choosing an appropriate evolution variable. And I will not go into the details here because I have few time, but this is described in the original paper. That's the one above here. And you can choose 3 different kinematics reconstruction schemes that lead to next to leading log accuracy if beta is chosen appropriately. You can actually stick to a dipole shower if you choose the right beta. You can use antenna type kinematics, which is similar to antenna subtraction kinematics in fixed order calculations, or you can choose a global recoil scheme. And this is all for E plus and minus. And this plot here shows tests of the next to leading log accuracy of the potential prediction for various observables, which are given here on the left, in comparison to analytic resummation calculations. And what the red dots here mean is that the NLL accuracy is violated at the precision level that is indicated here. The yellow ones mean that next to leading log is in principle violated, but you can't see it if you test it numerically. This is a numerical test. So they call this that the violation is masked at all orders because of the structure of the shower. I'm sorry about that. Let me just close Skype. The green means that everything is okay. Okay. So the logarithmic structure of angular order parton showers is known to be NLL accurate for global observables. However, also this one may be affected by the recoil effect, and this has been studied in this paper, following the initial paper from the Oxford group that I was showing earlier. And it was found that for the original kinematics reconstruction scheme, which they call QT preserving, everything is actually okay. The logarithmic accuracy is maintained, but there's actually an overpopulation of the hard emission region, and this can become very problematic. So what this paper shows is that looking at the logarithmic accuracy is a good thing, and of course absolutely necessary, but there are other effects that also need to be taken into account, because the parton shower is not supposed to only work in the logarithmically enhanced region, but across all phase space. And unless you want to match it to a very high precision fixed order calculation, which you may not have available, you better have a better description also in the half region. So then you can go to a Q-squared preserving scheme, which gives you a good description of the half region, but unfortunately this breaks the logarithmic accuracy, so you're in trouble. And then this paper actually devised a new intermediate scheme, which both maintains the logarithmic accuracy and gives you a good description of the half region. And you can see this here. This PT's preserving recoil scheme actually gives you a large overprediction in the half region of phase space for the 2 to 3 jet rate in the plus and minus, which is shown here in comparison to ALET data. Whereas this new scheme, which is the green here, does a fairly good job all across phase space and has much better agreement with the experimental data. And what you will notice is that this what is called the hard region in the paper actually extends quite a bit into the soft regime, certainly up to the point where you have B hadronization effect setting in.
Could you please go to your conclusions?
Okay. Okay, yeah, so then let me not go over this. There are interesting developments also. Let me just flash this one additional slide. There are interesting developments also in related to this color problem that I sketched earlier. This is kind of in combination between findings that were made in Lund about 27 years ago and a recent paper again from the Oxford group, which rectify this problem here and show how this backplane problem in the Lund plane and the simulation with the correct color factor can be solved in generic terms by just looking at the rapidity separation between the initial radiators and the emission. And with that, let me come to the summary. So deep elastic scattering is a precision laboratory for validating and calibrating our Monte Carlos. The simulations are possible to a very high accuracy nowadays, and we have at least next to leading order merged simulations available in all major generators, and we are looking forward also to include QED and electroweak correction. More generally, Monte Carlo generators are now being tested to their agreement, and so we can be confident that not only formally they are next to leading order precise and next to leading log accurate, but also that technically everything is working correctly, which has often been a problem in the past. So this is not trivial, as I'm pointing out here. And then there is a large body of work regarding to next to leading log accurate evolution, and this will allow a direct comparison to analytic calculations in the future. Next to leading order accurate evolution, which I have in the slide, so you can look at that, but I haven't covered it, which will give us the first realistic uncertainty estimate and will be a pathway to observable independent NLL accurate resummation and subleading color effects. Thank you. Barbara, I can't hear you.
Barbara, are you still there?
Oh, yes, sorry. Of course, I didn't unmute my mic.
Okay.
Thank you very much, Stefan, for your talk. And now we have 5 minutes for questions. I saw already one hand risen, that of Raghav. Please ask your question.
Yeah, hi. Very nice talk, Stefan. So I had one question on your slide where you compared the matching and merging, like the MC at NLO and the Boughezal.
Mm-hmm.
Yeah. So yeah, this one. So if you look at these dijet or trijet production cross section, they are dependent on kind of like the jet radius, right? So if, for example, I go to very small radius, then I will be doing some funny shapes to the spectrum, which brings in the effect of the parton shower, right?
Mm-hmm.
So to what order, or rather, which part of the actual calculation deals with this, this kind of dependence on the jet radius? Is it some kind of resummation, like next to leading log kind of calculation, or is it something more?
So that's a very good question. Part of this has been investigated in the paper that I was showing here. So we have done a pretty careful study of the jet radius dependence. You can see in the bottom plot here where we investigated the jet shape, we have 3 different radii, 0.4, 0.7, and 1.0. And you can see that for the different radii, there are differences here. So the ratio to the next leading order results here in the bottom panel differs and falls either above or below 1. And this is essentially a statement about how much radiation you include in your fixed order calculation versus the resummation, just as you point out. In order to get a good prediction at either very small or very large radii, you either have to go to a higher logarithmic accuracy in the parton shower, but not inclusively, like many people wrongfully assume, but fully differentially, because you're interested in out-of-cone effects, basically. So this is related to the point that I haven't covered, the simulation of parton showers at the next leading order, where you essentially, in addition to the single emission at leading order in the shower, you include the virtual corrections and the real emission corrections to the jet evolution itself at arbitrary order, and not only for a single jet. We are not at the point yet where we have this calculation fully complete. There are 2 different approaches, one by Peter Gans and Haitauli, who is in the audience, which is implemented in Vincia, but there are some pieces that are still missing for deep elastic scattering. This has been done for E+, E-. And there is one approach that has been done in Dios, which is in principle general. So this is available for VIL hadron colliders and E+, E-. But the collinear bits and the soft bits of the next leading order accurate evolution haven't been put together yet. So I would say, if you are interested in the precise jet radius dependence of these observables that I was showing here, stay tuned. We are not yet at the level where we can make a very reliable prediction with a good uncertainty band for this, for fully matched calculation. But you can look at the paper that I was showing here, because there is a region where the jet radius can be chosen such that possible corrections from the parton shower at higher orders that we currently don't have are supposed to be minimal. Right? There's always kind of a good jet radius in that sense.
Right. That's where I was kind of asking, and I was, I was quite interested in the last part of the talk that unfortunately didn't have time to cover. But yeah, it would be interesting to see if we go smaller than 0.4, because 0.4 you're still capturing, majority of the jet in your shower. So When you break it down to 0.1, 0.5 or something, then 0.15, then you're breaking into the actual shower, right? So that is where the shape differences will become very interesting, in my opinion. Yeah.
Now, I think the point was made. Let us give a chance to Pavel, who also rose his hand. But please, Stefan, give a concise answer. Thank you.
Yeah, Stefan.
Pavel, please.
Yeah, thank you. At the EIC, most of the events will have very low Q. So how do you plan to implement hard twist effects as well as other low energy effects that will be relevant in this case?
Okay, so something that I'm not quite sure I'm giving the answer in the right direction, but something that I haven't spoken about is the transition between deep elastic scattering and photo production. This is in principle understood and has been implemented by the older Lund Monte Carlos, and this will have to be re-implemented in the current Monte Carlos, which so far have focused mostly on LHC physics. I'm not sure if that answers the question.
Okay, thank you.
Well, no more hands risen, so thanks again, Stefan, for a very good talk. Thank you. And then I would like to invite Radja Boughezal from Argonne to tell us about highlights, to show us highlights of precision QCD at the LHC. Please, Radja.
Thank you, Barbara. Let me try to share my screen.
I will warn you 5 minutes before the end.
Okay, thank you.
Thanks.
Okay. Can you see the slides?
Yes, we do see the slides and we hear you well.
Okay, thank you very much. Thanks for the invitation to give this talk. As was just announced, I will be giving you some recent highlights of precision QCD at the LHC. And in fact, I will not just limit myself to the LHC. Somewhere near the end, I will show some recent results that are relevant for future colliders such as the EIC. So let me start with the motivation. Why is precision relevant now more than ever? There are multiple reasons, and I will just give you some of them here. One of them is that we need precision QCD to correctly interpret data, especially precise data. An example that shows this is the Higgs cross-section measurements. This is a plot from Atlas that shows you the signal strength for Higgs production in various modes, and then the combined one from run 2 and run 1 at the bottom. As you can see from run 2, we have already included N3LO QCD results for the dominant production mode, which is the gluon fusion. We are right now in agreement with the standard model, and there are 3 sources of uncertainty that are shown here. We have the statistical one, which is the largest. We know that this will go down as we get high precision results from future Halloween-Oz the LHC measurements. And you can see that it's followed immediately by the theory uncertainty here, which is the second largest error. So even though we have included N3LO results, there is still room for improvement, and this actually emphasizes the need for a continuous progress on the theory side. Another reason for precision QCD predictions is the fact that we need them in our search for new physics, especially indirect searches. This is a plot that shows you jets plus missing energy in the final state, which is a hallmark for many models beyond the standard model. We have a few shown here. We have Susie, we have Derek Matter. They are shown here in these dashed lines. And you can see that there's a lot of background from the standard model. The one thing that this plot emphasizes is that the slope of the standard model background is different, is harder than what the new physics models predict. And so it's very important for us to understand the slope of the standard model very well to be able to see if in, for example, regions of high ET miss, we have some discrepancy between the standard model and new physics. And this is where tools that are based on solid predictions from QCD, such as merging or matching fixed order results to pattern showers, become important. Another motivation is the fact that in our quest to understand QCD, several new ideas came out. It's a very rich field, actually, and one of them is jet substructure techniques. So we are today able to look inside the jet and we are somewhat able to see if it resembles a QCD jet or if it comes from new physics. This is just an example of a search for a heavy Z prime in the TT bar channel where the tops are boosted and jet substructure techniques become important in disentangling signal from background. So as I said, these are just few reasons to motivate this, and I hope I get my point across. Let me move towards the formalism or framework we use for predicting cross sections. It's called collinear factorization, where we predict our harmonic cross sections as a convolution of pattern distribution functions, which are universal, non-perturbative. We have patterning cross sections, which are process dependent, and we can calculate them perturbatively as an expansion alpha S. So when we say NLO, NNLO, etc., we are referring to coefficients of alpha S in this perturbative expansion. And of course, this factorization is true up to some powers of lambda QCD over the scale of the problem. Let me just shrink this, okay. So what is the current state of the art? Today, we know a lot of, or many relevant NNLO or processes at the NNLO level differentially, standard model cross sections, including jets in the final state. We have already the first prediction for a 2 to 3 process that is PP to 3 photons. And we have a few N3LO cross sections, mostly inclusive for the time being. That's for GGH, VBF, and Radja. And so our goal is actually to increase the precision of our predictions, both for signals and standard model backgrounds. The aim is to be able to disentangle BSM effects indirectly through precision tests of the standard model. Now, obviously, I will not be able to cover all the recent results and updates due to the limited time, so I apologize in advance if your work is not here. Let me start with the first result. That is the fully differential cross-section for blue to Higgs to gamma-gamma at N3LO. It's, of course, a big milestone. We are excited about differential results because they allow us to impose selection cuts similar to what is imposed experimentally, and therefore we are able to compare apple to apple. So, as I said, this is the first fully differential result at N3LO. It was obtained using the projection to Born method. It's a way of extracting inferred singularities from our cross sections. And so before we go into studying these plots, let me just summarize some of it. You will see some items you will see here. We have the N3LO K factor. This is the inclusive K factor calculated as a ratio of the inclusive cross section at N3LO and NNLO. There are some cuts on the photons, the leading photon and the second photon. And there is also a window in the pseudo-rapidity of the photon that has been cut, which corresponds to this hashed line that you see in here. All the scale uncertainties that you see in here are obtained by varying the renormalization and factorization scales around the standard value, which is m Higgs over 2 here by a factor of 2. Okay, so let's look at the plots. We have 2 plots here. One is the cross-section as a function of the pseudo-rapidity of the photon, and the second one as a function of the difference in rapidities of the photons. The blue result is the NNLO old result. Red is the N3LO differential result. And there's another quantity that they are showing here in yellow, which is the scaled NNLO factor with the inclusive N3LO K factor. And one reason this is shown here is that often, this is an approximation that is often used when we don't have higher order differential results, we have a lower order, and we have an inclusive K factor at the higher order. So quite often such approximations are used to try to mimic the missing higher order result at the differential level. Now, sometimes that works, and it gives you a realistic description of the differential results, sometimes not. And we are here in a situation where we see both cases. So on the left, especially if you focus on the lower part of the plot, which is the ratio to NNLO, you can see that the actual N3LO differential result is consistently higher than the approximate NNLO result scaled with the N3LO inclusive K factor. If you go to the right side, you see that the 2 results are actually in agreement. They are on top of each other pretty much throughout the entire range until this bin here, the last bin where there is some perturbative instability. So these are 2 cases where you could see that the approximation on the left-hand side doesn't work, on the right-hand side, it works. Let's move to Radja at N3LO. Radja is a very interesting process. It has a clean final state signature, which makes it an ideal candidate for luminosity measurements and detector calibration. Of course, it's one of the important processes for PDF fits as well. And we understood it, or it has been studied in detail on the theory side. We have NNLO QCD corrections, supplemented with electric effects, mixed QCD QED effects. Measurements on the experimental side are also very precise. So this is a good process to really use to try to understand new physics effects eventually. Now, very recently, the N3LO QCD results, inclusive ones for Radja, became available in 2 cases. One is through the exchange of the virtual photon and then charged current contributions as well. We still don't have the case with the Z. And the results are actually shown in this table here. You see the K factor at N3LO, and you see various sources of uncertainties, the scaled PDF plus alpha S, and there is a third source of uncertainty that I will just discuss in a bit. So the K factor actually shows that the n-cubed LO corrections have shifted our results by roughly 5%, around 30 GeV for Q, and otherwise the change varies between, or the increase varies between 2 to 4%. We see the PDF plus alpha S uncertainty. This is, as we know, is practically a propagation of the experimental error. There is a third source of uncertainty here, delta PDF theory, which is coming from the fact that we don't have yet N3LO PDF fits. So if you are doing a next to next to next read order calculation using NNLO PDFs, there is an uncertainty associated with that. And this is how what the authors have estimated. It's roughly 2%, and it's actually pretty close to delta PDF plus alpha S. So the point here is that such uncertainties should not be neglected as we move, especially as we move to high precision data from the LHC. There is another point that was made in this work. If scale uncertainty was accurate, you would expect that it should contain, that the error band at certain order contains the missing higher order corrections. Now, what we see from this process, the Jurian case, is that there is a range of values of Q, roughly 50 all the way to 400, where we see that the blue and the red bands don't overlap. It's a minimal lack of overlap, but there is no overlap. So this can be due to many reasons. One reason could be that the scale uncertainty is not an accurate way for estimating the next order or missing higher order corrections. And so there is a need to think of different ways of estimating theory uncertainties. Okay, let me move to NNLO corrections. In the last few years, we have seen significant progress at the NNLO level for differential results. As you can see, between 2014 and now, there is an explosion of results, and even processes with the jet in the final state have been provided at NNLO. What's more interesting is that many of these results have actually been provided by several groups, in particular for W plus jet, Z plus jet, Higgs plus jet, where we have a great opportunity to look at these results, compare these complicated calculations, and so on. So that's actually great. So what's the current progress? Right now, we have many important fully differential cross-sections for color singlet processes, such as PP to Higgs, vector boson, diphoton, Higgs production in associated with a vector boson, diboson, and 3 photons. We also have the cross-section for TT bar at NNLO, and we have several processes with the jet in the final state that are also available at NNLO differentially, including Higgs plus jet, WNZ plus jet, photon plus jet, dijet. We have some topologies for Higgs plus 2 jet and di-Higgs plus 2 jet at NNLO, the so-called VBF approximation, and we have also the result for EP, electron proton to 2 jets. So as you can see, it's a rich set of results, and we are pretty much at the stage where we can sit and ask ourselves, how can we go beyond where we are today, beyond 2 to 2? And there are actually multiple ways. One of them is to go to these results and see in what approximation some of them have been provided and see if we can improve it. That's the case, for example, for Higgs plus jet at NNLO, which was calculated in infinite and top limit. Another way would be to go beyond 2 to 2 by looking at some of the relevant 2 to 3 processes. And probably the first that come to mind is TTH, as you can see from this plot from 2018 from Atlas. Right now we have NLO predictions, including QCD and electric effects. Compared with the large uncertainties from data, we are currently in agreement, but you can see that once this error bars reduce with future measurements, there will be some sort of discrepancy between theory and data. So there is clear need to improve the prediction and push it to NNLO for TTH. So doing this actually requires progress on other sides, in particular calculating amplitudes, two-loop amplitudes, either with multiple particles in the final state or with more scales in the problem. So right now there is a strong activity covering both of these aspects. 5 particle two-loop amplitudes, which would be needed for the calculation of TTH, for example, are being pursued by many groups. We have currently an active set of studies, including analytic and numerical methods. We are also witnessing a lot of progress from multi-scale two-loop amplitudes with massive internal particles. This is, for example, what you would need to improve the precision of Higgs plus jet, which was done in the infinite and top limit. And again, there is progress here. People are faced with all sorts of complexities like dealing with complicated mathematical structures like elliptic integrals. Okay, so let me show you as an example the first 2 to 3 result. This is PP to 3 photons. Atlas has measured the cross-section for 3 isolated photons. And as you can see from the plot, the upper or middle part, if you just look at the blue result, which is the NLO1 compared to data, there is a disagreement. Once you include the NNLO result that was provided recently, you could see that the agreement with data becomes much better. Now, this result has also been provided in standard approximation called the leading color approximation that simplifies the calculation of amplitudes. So there is a room for improvement again here, but it's an important first result. The other thing that I would like to mention here is that this is a simpler process than TTH. It has a simpler infrared structure, less scales in the final state. So still, to go to the TTH at two loop level, we still need to have some progress on the theory side, in particular from the amplitude level. Okay, so let me move to matching NNLO and pattern shower. Stefan has already covered part of this discussion, so I will have a very brief 2 or 3 slides on the topic. As we know, next and order cross sections provide precise predictions, but they are limited to low multiplicity final states and pattern level. Pattern showers are less precise, but they have more realistic description of our process, including harmonization effects, multi-party interactions. We want to merge the best of these 2 words. We want to get the benefit of the best of these 2 words, and that is done. One way that it is done is through matching NNLO to pattern showers, or what I denote here as NNLOPS. So this would give you a good perturbative description of your, a good description of your process, precise description of your process with realistic, with the option of having realistic cats and things like that on the final state. So what's the current state for matching NNLO and pattern showers? Right now we have 3 methods that exist for doing this. For color singlet production, these are the NLOPS, MinLOPS, and Geneva. Recently, the MinLOPS approach was also extended for heavy quarks, in particular PP to TT bar. So that's an important step. However, the path to extend these methods to a generic 222 is not yet clear. Just like in the fixed order case, there is work that has to be done to see how we can really do the matching for any 222 process. So this is now an example from the calculation or the matching that was done for the TT bar case. In fact, the plot speaks pretty much for itself. So in blue, you have the MinLOPS result, MinLO prime, which is matching NNLO to a pattern shower. MinLOPS is matching NNLO to a pattern shower. NNLO is the pure fixed order result, and we have CMS data in here. And if we look at the bottom part of the plot, where everything is normalized to MinLOPS, comparing the MinLO prime result in gray to the blue, which is MinLOPS, you could see that that MinLOPS has shifted the result from MinLO prime by 20 to 10%, 20 around MTT bar of 400 GB or so, and for most of the range, it's roughly 10% difference. The error bands have reduced significantly in going from gray to blue. If you compare the fixed order result in red with the blue, you could see that the 2 of them are in pretty much good agreement for most of the range of the TT bar mass, except from the range around MTT bar of 500 GeV, where there is a difference of 10% or so. The error bands differ slightly. That's because when you also have the pattern shower, there's a scale associated with the starting point of the pattern shower, whose uncertainty has to be taken into account. So you expect to have larger uncertainty than just looking at the fixed NNLO result, which has the usual renormalization and factorization scales. Okay, so let's move to PDFs. PDFs are a critical component of the LHC precision program. They are needed for all aspects, from measurements to searches. For example, if you look at the WMAS, you could see that the PDF uncertainty is half of the total uncertainty. For Higgs cross-section, one of the largest uncertainties is PDF plus alpha S. For high resonant mass searches, you could see that in that high range, the PDF uncertainties are large and definitely need improvements. So overall, there is a clear need to keep improving them to benefit from the upcoming LHC precise data. The current status is as follows. The 3 major global fitting groups, CTEC, MSHT, and NMPDF, have incorporated multi-differential W and Z and TT bar data from the LHC. We also have, they also have combined DIS data from the H1 plus 2's results. ABM16 has been updated to include non-resonant gamma star Z data for the first time in 2019. Most processes are now incorporated with full NNLO QCD corrections. NNO electric corrections are included when available, and there are various methodological improvements by the various groups. Now, the impact of this work depends a lot on what PDFs you are looking at. So if I look at the strangeness PDFs and we compare the old results with the new ones, you could see that in going from left, which is old, to right, which is new, there is a significant improvement in the strangeness PDFs. Error bands have reduced. There is a good overlap between the various error bands from the various groups, and that's good. When you look at other processes such as, or at other patterns such as blue ones, you could see that the situation is not as good. In going from left to right, you could see that the overlap between the bands of the various PDF fits could be improved in the future. So there is room for benchmarking and improving these results. The next thing that I wanted to cover in here is theory uncertainties in PDFs. One thing that we usually refer to is PDF plus alpha, as those uncertainties are actually coming primarily from the experimental data. There is another source of uncertainty associated with the calculations that go into the fit that is usually not accounted for. But recently, NIPDF has made one step towards incorporating this in the PDF fits. And the result is shown on two quantities in here, or two cross-section, GGH and VBF, GGH on the left, VBF on the right. And I will focus on the n-cubed LO case. Blue results are the PDF fits before incorporating the theory uncertainty. Red are coming using fits that incorporate the theory uncertainty. Light blue corresponds to scale uncertainty, dark blue corresponds to PDF uncertainty, and the same for the red. Now, when we look at the GGH case, comparing the fit without the theory errors with the one with the theory errors, you could see that the PDF uncertainties got slightly larger after including the theory uncertainties. The standard value did not change by much for GGH. For VBF, on the other hand, you see that while the uncertainties did not change by much from the PDF, you could see that the standard value changed, went upward by roughly 1% in this case. So there is an impact. So let me move towards the interplay between precision QCD and BSM searches.
Radja, you have 5 more minutes, please.
Thank you. Yeah.
That's okay.
As we know, there is no direct evidence so far of new physics at the LHC. So a reasonable assumption is to say that it's probably heavy. There is a way of going beyond the standard model that is minimal, and it uses the effective field theory approach. It's the SMAFT approach, and it allows you to utilize data from high energy machines like the LHC and low energy experiments. And so what you do is, in addition to the standard model Lagrangian, you add 6 and 8 dimensional operators, of course, suppressed by the relevant powers in lambda, where the lambda is the scale of the new physics at which UV completion is important. So the question here is, how do these higher dimension operators affect our predictions? And one process I have described at the beginning of my talk is the Drellian, which I said is understood with high precision, both from the theory side and the experimental side. And the idea, or the question, of course, is how do we leverage this precision? And one thing we could do is to look at the angular dependence of leptons in Drellian and see the impact of high dimension operators on the angular distribution. And there is a formalism that has been developed 4 years ago that tells you how to do this. Roughly, you can expand your differential cross section in terms of the spherical harmonics up to L equals 2. L equals 2 because we have a Z with spin 1. So at the amplitude level, L is equal to 1. But when we square the amplitude, L equals 2. And this expansion is shown here in terms of this AI coefficient. Now, when we included higher dimension operators, it turns out that there is a novel effect that hasn't been accounted for coming from a certain set of dimension 8 operators. And those are operators that have 2 derivatives. And this is just a subset of them. And so you find that you have to extend this expansion to L equals 3 spherical harmonics. And this is done by adding these coefficients BI in here. And what you could do is study the impact of this on these coefficients. So we will see the impact on the B0 coefficient on the next slide as a function of the lepton invariant mass. And so what we do here is turn one coefficient on and then set all the other ones to 0. And you could see the impact of that here clearly. There is a significant deviation with respect to the standard model. Now, one question one might, of course, ask is, can these effects be generated by QCD corrections or electric effects? And the answer is no for QCD. And yes, they can be weakly generated by electric effects. And in fact, on this plot, there is a line here in green, which shows you the leading electric effects in the standard model. And you could see that they are much smaller than the deviation you see from these other operators. Let me move to a topic that is very fitting to the nature of this conference, puzzles in the proton structure. As was pointed out in earlier talks, even after several decades of studying the proton, we don't understand simple aspects of QCD still to this day. Questions like how is the proton spin formed from its microscopic constituents, or how are the C quarks and gluons and their spin distributions in space and momentum inside the nucleon distributed. We don't know exactly how to answer these questions yet. We know that the proton spin is 1/2. We know that it's made out of the quark spin, gluon spin, and orbital angular momentum. How much of each of these contribute is not yet clear. So our goal is to have a precision determination of polarized PDFs. And one quantity that was measured at RIC is the spin longitudinal single spin longitudinal asymmetry for W. In fact, the definition of the AL is very simple. It's the difference between the polarized cross-section for the polarized proton divided by the sum. The leading order expressions for the positively and negatively charged W are shown in here as a function of the W rapidity. They are pretty simple here. And you can see that when you go to the region where the W rapidity is very large, where X1, Bjorken X1 becomes much larger than Bjorken X2, these expressions simplify. Valence quarks dominate, these expressions become much simpler. In the region where YW is much smaller than 0, X2 becomes larger. And again, these expressions here simplify to what we see here at the second line. And you could see that it's this region of YW less than 0 that is sensitive to polarized C quarks. From measurements that were done experimentally, we know that AL for the negatively charged W is positive at low values of the pseudo rapidity of the electron or the lepton, which is of course correlated with the rapidity of the W. AL for W plus is negative. So taking this information into account and looking at this line here, taking the difference between AL W minus and plus, we deduce that delta U bar minus delta D bar is positive. And so this gives us a hint about the flavor structure of these polarized C quarks. We went ahead and we calculated this asymmetry at next to leading order for the first time. The results are interesting because the asymmetry was very stable under perturbative corrections. What you can also see from here is that the scale uncertainty is much smaller than the PDF uncertainties, which are here available only at NLO. These are polarized PDFs. So you could see that this observable provides really a chance for us. It becomes an important observable for possible future fits at NNLO for polarized CPDFs. Okay, so a precision determination of polarized PDFs will first come from the EIC by looking at these plots, which have already been shown earlier. You could see that polarized gluons, the current uncertainty of polarized gluon PDFs or singlet quarks is much larger than what we expect to see at the EIC with various center of mass energies. And so we want to do what we have done at the LHC. At the LHC, we have determination of the PDFs at the NNLO level, and that has played a role in our way of understanding data. EIC will provide precision data as well in the future, and we want to have predictions that match the expected precision from data. We want to have something similar to what has been done at the LHC. And one thing I wanted to emphasize with this plot, which corresponds to inclusive jet production at NNLO for the unpolarized case, it shows you the contribution from various partonic channels and the fact that different regions of jet phase space can give you access to different PDFs. If you look here, you can see that there is a region that is dominated by the quark. There is another region that is dominated by the gluons. And so you could use your data and such results to extract information about their PDFs. And so in this spirit, recently, a new result for jet production in polarized DIS has been calculated at NNLO. It doesn't have yet direct or result photon contributions, but it's an important first step. And overall, what you see from the plot is that this NNLO corrections shift the distribution towards lower value of PT of the lepton and higher values of the rapidity of the lepton or the rapidity of the lepton. And overall, there is a good perturbative behavior. And this brings me to the summary of my talk. So in the last few years, we have witnessed significant improvements in the accuracy of the standard model predictions for a host of processes. NNLO differential distributions are the standard today for 2-2 processes. We have first NTLO results. It's important to continue this precision program in the future, given the precision of LHC data that we anticipate. We can gauge sensitivity to heavy new physics through EFT approaches, such as MEFT, and I've showed you an example of the possibility of being sensitive to some novel experimental signatures through such frameworks. And of course, there is a great synergy between LHC and EIC. Several tools and methods that have been applied for the LHC can be applied to the EIC. And we are looking forward to an exciting new results era and advances. Thank you.
Thank you very much, Radja, for this complete and good talk. And then I invite questions and comments to it. You may write it on the chat, you may raise your hand. And I see already 2 hands risen. First is Ignacio. Please ask your question.
Oh, probably Joy was first.
Oh, well, it says that it should be chronologically here.
Okay. So I put my camera on. Hello, Radja.
Hi.
Thanks for a very nice talk. I have some simple question about Drell-Yan. And you said that if one uses N-cube-LO calculation with the N2-LO PDF, there is a shift of 2%.
No, not Drell-Yan. That wasn't Drell-Yan. That was, are you confusing the VBF and GGH slide, or what are we talking about? Sorry, let me get you this slide.
No, before. You had a table between the shift.
Yeah, I'll get to it just a moment. Where are we? Yeah, here.
Yeah, please.
Yeah.
So this is a theoretical error. Theoretical error here, as far as understood, is you make a fit of Drell-Yan, I think, and or no, a prediction of Drell-Yan. In one case, you use N-cube-LO perturbative calculation with NN-LO PDF.
Yes, so the error indeed comes from the fact that you have an N-cubed-LO calculation, but NN-LO PDFs. Yes, that's where this error comes from.
Okay. Is this error homogeneous in X or?
So I can tell you how the authors say they have provided or calculated it. So they take the NN-LO cross-section, calculated once with the NN-LO PDFs and once with the NLO PDFs, take the difference and divide it by 2. That's this uncertainty that you see in here. That's what they say in their paper.
I see. Okay, so you have there's no clue. And
I don't know, you have to look at their paper. That's what they say, actually, how they provided it. In earlier days, what they used to do is take the structure function at N3LO, evaluated at the center scale, minus the structure function at NNLO, evaluated at the same scale, divided by 2. That's what they used to do in the older days. I was looking at their paper yesterday, and then in this paper for Drell-Yan, that's what they say they do. They just take the NNLO cross-section, calculated once with the NNLO PDFs and once with the NNLO PDFs, take the difference and divide it by 2.
Okay. And another curiosity, why in this Drell-Yan at N-cube-LO, you said there were calculation for vector boson as a W, as a gamma star, but not as a Z star. What's the problem with the Z star?
I don't know. You have to ask them. They have the result for gamma star. They have the charge current yet, not yet the Z case. I mean, the Z is typically slightly more complicated because you have to deal with things like gamma 5 and so on. But I don't know if they have other sources of complication. That's a question for them, for Claude and his collaborators.
Okay. That's all. Thank you.
One of our cafes on Zoom.
Sure.
Okay. And now, Joy, please, your question.
So thank you for the very nice talk, Radja. So I have 2 comments and a question. So first, a comment on the N-cubed-LO differential Higgs to gamma gamma and the instability that you pointed out. So that's due to the fiducial cuts that we made in Atlas, regarding the PTs of the photons and, well, to some extent as well, also the rapidity cut that we made to exclude the region from 1.37 to 1.52. It would be interesting to actually do that calculation for a slightly higher PT where these fiducial cuts are not going to have the same type of impact. And I'm sure if that was done, then you would probably see a stabilization of the scale dependence over the full rapidity range.
That could well be. I don't know if the authors are indeed looking at that, but I agree with you. It's due to the cuts. Basically, you are suppressing the lower order cross-section, and the phase space opens up only by going to higher orders and emitting additional radiation. However, you become very sensitive to your soft radiation which leads to large logs that if you don't resum in this bin, you will see this instability. I don't know what happens if they extend the range. This is something for sure they probably can do indeed.
Sure.
Yep.
And I just thought of that, just actually during your talk. So I'm not sure if they're thinking about that or not. The second comment is that you had mentioned about the PDF uncertainty and how crucial that is to whenever we're trying to do precision physics, for example, with the Higgs. So I just wanted to advertise a talk that Tom Cridge is giving tomorrow, I believe, on a benchmark exercise that we're conducting of the 3 global PDFs in order to try to first of all, understand any differences among the 3 PDFs and to come up with a combination PDF for LHC 21, that's similar in spirit to PDF for LHC 15. And again, this benchmarking is hard work as it was in 2015, but so far, I'd say it's been very rewarding. We're trying to understand different aspects of PDF determination.
And please answer in a concise way because we have 2 more questions.
The answer is yes, I agree with him. This is highly motivated for sure.
Okay, and okay, here's my question. It'll be a quick question. So you pointed out that many higher order calculations have only been done at leading color. Do you have any calculations in mind for which you suspect that next to leading color might be a non-trivial contribution?
I don't think many calculations have been done in the leading color approximation. The one that we know for sure is PP to 3 photons. I'm not sure what the contribution of the missing terms will be. So right now you practically have the contribution of the planar topologies. So the leading color approximation is specifically done to simplify the calculation and equal these planar ones. What's missing are the non-planar topologies. I'm not sure how much of an impact that will have. I can't answer that really right now. I need so many calculations. There used to be some approximate calculation for Dijkjet, I believe, but I think they have included more than just the leading color term.
All right.
Yeah.
Mandy Cooper, please, a short question.
It's actually just a comment, Barbara, and that was just to say that it's great to have N3LO calculations now, but we've already had NNLO calculations for some time. But when it comes to PDF fitting, you need them in a form which is practical to do an iterative fit. And it's a long time between the calculation coming out and people producing the kind of grids of them that we need to do PDF, convolute with PDF fitting. We've had to put up for a long time with doing kind of K-factor approximations, which are not really ideal. So great, but just a warning, it doesn't mean there'll be N3LO PDF fits tomorrow.
That is absolutely correct. It's true that even at NNLO, things are tough because to run these cross sections numerically, it takes a lot of CPU, a lot of time. You have to control things numerically in an incredible way, which is tough because of the nature, the complexity of the process. So yes, already at NNLO, things are tough enough. And no one's
okay, that's all I had to say. Thanks.
Well, thank you, Mandy. Now my question, Paul Newman, have you given up your question?
Yes, Barbara, it was sort of covered in Joey's questions. So.
All right, very good, thank you. So thank you very much, Radja, for your fantastic talk. And then great thanks to all the speakers of today, because we all, most of us, know what does it mean to prepare such a talk for. So thank you very much for your great effort and very, very good delivery of those talks. Thanks. Goodbye.
Thank you. Thanks.
Hey, we are at the end of the session. Let's plan to meet tomorrow, 8 o'clock Eastern time, 2 o'clock European, 12 o'clock China,